We introduce SAGE, a framework aimed at language-guided generalizable articulated object manipulation. Imagine that you bought a new blender for your kitchen. To make juice with it, you need to truly understand the semantics and functionalities of its parts, in this case, the container. To turn on this blender, the robot needs to press its container and it will blend the ingredients in it. Here we understand the part at the semantics level as a container, just like the container in the coffee machine, it is used to load ingredients. But when we want to turn on it, we consider the part at the action level as a part to be pressed, just like a button. We introduce our SAGE framework to understand parts at both semantic and action levels. Our pipeline takes human instruction as input and interprets it into a semantic part and an action program. The action program is a triplet of semantic name, joint type, and state change. To achieve so, we first mix the domain specialist model, GAP-PartNet, and the general-purpose large vision language model, BARD, to generate a context-aware scene description. The scene description along with the human language instruction and the optional user manual of the object are jointly embedded in a template prompt and are then input to GPT-4 to generate semantic parts names and the action programs. We further ground the semantic parts into the target actionable part. Here for this blender, the semantic part is a container and the actionable part is a slider button. We then estimate the part pose along with the press motion. Finally, we execute the action and turn on the blender successfully. Here is another task. The instruction is to open it, without the object name. The same as before, we first generate a context-aware scene description. Then semantic parts and action programs. With our grounding model, we get the actionable part pose and joint. But attempts to open the door by utilizing the handle while it was closed failed. This is because the microwave cannot open the door directly using the door, but needs to use a button to open it. We give feedback on the target part pose and actual part pose to our planning model GPT-4 and it finds the failure and decides to replan. This time, with its extensive prior knowledge and part analysis, GPT-4 says pressing the button to open the door slightly followed by an action to revolve the door. And the new policy executes successfully. We show more video clips to demonstrate the diversity and generalizability of our method. Our method can handle diverse and even vague instructions and has a strong generalization ability. Thank you for watching. Please check our paper and website for more details.